Okay. Can you see it? Hello? Can you hear me?
Yeah, I can
Okay.
hear you.
Okay, so thank you so much for the kind introduction, Chairperson, and thank you very much for the organizers and for giving me an opportunity to introduce my work. And my topic is about the local detection phonon-magnon coupling using a acoustoelectric current that is a bit different technique and to detect the interaction between acoustic wave and spin waves. And my name is Hiroki Matsumoto from the Kyoto University. But this project is basically what I did when I was a PhD student in my previous group in the University of Tokyo. So let's get started. The magnetization dynamics is a collective precession motion of magnetic moment in a ferromagnetic material. It is excited by applying the microwave field when the ferromagnetic or spin wave resonance frequency matches to the microwave frequency. Magnetization dynamics can be driven by also using the phonon-magnon coupling, which we focus on this our study. When acoustic wave, the propagation lattice distortion is excited in a ferromagnet, an effective microwave field is induced in ferromagnetic material by the magnetic-elastic coupling. In this case, magnetization dynamics propagates as a spin wave with finite frequency and wavelengths, and that is identical with the frequency and the wavelengths with the acoustic waves. For the study of phonon-magnon coupling, the surface acoustic wave device SAW is widely used. SAW is an elastic wave that is localized at the surface of the solid. A SAW device has typically this kind of cone-shaped electrode, so-called interdigital transducer, IDT, developed on the piezoelectric substrate. When when an electric field is applied to the IDT, electric field is converts to the strain and propagates as an elastic wave. The acoustic wave transfers to the ferromagnetic field on the wave path and then drives a spin wave. A conventional approach to detect this spin wave coupling is so-called the SAW transmission spectroscopy. The first SAW is excited at IDT by applying an electric field, and it traverses the ferromagnetic field, and then finally SAW is inverted to the AC voltage at the IDT. When the spin wave resonance frequency matches the SAW frequency, the SAW energy is transferred to the magnetization dynamics, and then it is detected as a reduction of the SAW power. And we can probe this as a reduction of the SAW transmission. And basically, we often use the vector network analyzer, VNA, to conduct this kind of measurement. IDTs are connected to the VNA, and the scattering matrix in this system is measured. This method is well established and so widely used to sense a phonon-magnon coupling in a surface acoustic wave device. But actually, the fixed range of the frequency in the detection is limited by the design of the IDT. So we propose a new way to detect the phonon-magnon coupling in a ferromagnetic field. And we use a so-called acoustoelectric current as a SAW detector. So first, SAW is excited at the IDT and it traverses, and so finally it generates acoustoelectric current in a metallic film, and this current is DC current, so it can be measured from as a voltage in a metallic film. When magnetization dynamics is excited, and then the SAW energy is transferred to the magnons, and then so the power of SAW is decreases, and it is detected as a reduction of the DC voltage in the metallic film. So this metallic film is the simple shape, and ideally can detect SAW with any frequency. We aim to demonstrate this detection scheme in our work. This is a schematic of a device and setup. IDT is composed of the copper layer, and a nickel film is deposited on the center of the wave path. In the vicinity of the nickel film, a pair of metallic antenna of the tantalum made of a tantalum film is fabricated for acoustoelectric current detection. All structures are developed by using RF magnetron sputtering, photolithography, and the lift-off process. An external magnetic field is applied in the film plane to modulate the spin wave resonance frequency of the nickel film. We perform all measurements at the room temperature. To use the acoustoelectric current as to prove the soul power, we need to know the relation between the acoustoelectric current and the soul power. In the previous study, they reported that acoustoelectric current show linear dependence on the soul power. And the specular of the acoustoelectric current showed a similar dependence on the frequency as that measured by the VNA. And the sign of the acoustoelectric current reverses when the propagation direction is changed. So we make sure that these characteristics of the acoustoelectric current is shown in our device. First, we measured the transmission specular and the frequency dependence of the DC voltage in the metallic antenna. Here, an external magnetic field is applied not to excite the spin wave. And we observed that specular with a very similar shape with a peak around the 2.35 gigahertz. Next, we investigated the power dependence of the acoustoelectric current. Then we observed a very beautiful linear dependence on the RF power of the DC voltage measured at the metallic antenna. And soul power is known to be proportional to the input RF power. So now we know that the DC voltage in the metallic antenna can be used as a soul detector. Based on that, we demonstrate the detection of the phonon-magnon coupling by measuring the acoustoelectric current as a function of magnetic field. We observed a clear reduction of the DC voltage measured at the right antenna. Here, the voltage at the right antenna shows the soul power after propagating in the nickel film, and it is proved as the decrease of the acoustoelectric current at the right antenna. Next, we compare this result with a conventional detection scheme with using VNA. The soul transmission and the DC voltage at the right antenna were measured as a function of the magnetic field and the field angle. We observed a very similar dependence on the field dependence for the result of between the VNA and the DC measurements. This is clear evidence that the acoustoelectric current can be applied to prove the phonon-magnon coupling in this device. At first, we expected that the DC voltage at the left antenna does not depend on the magnetic field because the left antenna basically should probe the soul before transmitting the nickel film. However, the voltage increases at a certain magnetic field. So when we need to consider the other contribution to this effect, because when we only consider the transmitted soul, this result cannot be explained. So we discussed the effect by taking the reflected soul into account. First, the soul is excited and then propagates, and this generates a acoustoelectric current at the left antenna, and it traverses the nickel film, and then after that, it has the information of the spin waves at the right antenna, detected at the right antenna, and then this is shown as a decrease of the DC voltage at the right antenna, and depending on the magnetic field. Now we assume that soul is reflected at the nickel film and also at the right IDT. And when we consider this effect of reflected soul, and then the reflected soul generates the negative sign of the acoustoelectric current at the left antenna. And this reflected soul also experiences the energy transfer because of the phonon-magnon coupling in the nickel film. And then it appears as the increase of the DC voltage because of the reduction of the reflected soul with the negative acoustoelectric current. So in this way, we now can detect the effect of the phonon-magnon coupling not only for the transmitted soul, but also for the reflected soul. But if this scenario holds, the increase of the DC voltage at the left antenna should depend on the magnetic field in the same way as that for the transmitted source. Interestingly, however, the resonance field and line width for the reflected source are different from those in the transmitted source, and we still don't know why. But the result may imply the nonlinear phonon-magnon conversion process start because the metallic antenna should detect the source in any frequency, so the possible frequency conversion process may occur, but we need to study more to identify the origin of this effect. Let me summarize my talk. We demonstrate a simple detection scheme to probe the phonon-magnon coupling in a ferromagnetic thin film with a surface acoustic wave device. We measure the DC voltage in a thin metallic film to probe the acoustoelectric current to use it as a source detector. We measure the DC voltage in the metallic film to when the source frequency matches the spin wave frequency, then the spin wave is driven and the source power is used to drive the spin waves, and then it is detected as a reduction of the DC voltage in the metallic film. We observed this effect of phonon-magnon coupling for not only the transmitted source, but also for the reflected source. Our results show the potential of this scheme to study the interaction between the source and the spin waves in a surface acoustic wave device. Thank you for your kind attention.
Thank you, Dr. Matsumoto. So let's move on to the question section. Does anyone have a question, comment? Okay, only 1 minute left. Okay, can I ask something from me? So I have a question about the shift of please go to the 13. Okay, here. Next page, please. So this nonlinearity is occurred in the just the magnon or in the conversion phonon to magnon process?
Yeah,
yeah.
So we still discuss the origin of this effect. And actually, if the resonance frequency is identical between these transmitted to the reflected wave, then the resonance field should, agree. But actually, yeah. So maybe because of the nonlinear effect in the phonon-magnon coupling, but basically, when so nonlinear effect is observed when you apply the a very large input power, but in our experiment we input around 1 milliwatt or 10 milliwatt. Yeah, so 10 milliwatt power. We don't think that it's enough to excite such a kind of nonlinear dynamics. So and also there are some possible explanations, but actually, yeah, we cannot. I cannot say now. Yeah, and we're still discussing.
Okay, I'm looking for.